Hello everyone, welcome back. My name is Dilleswara Rao. I'm from Aeronautical department. I've been giving lectures on automatic control of aircraft subject, which is coming on BTech course. So from the last few classes, we have discussed on longitudinal static stability, and it's a longitudinal static stability equation derivation and its significance and its usages and stability derivatives and its significance also we have discussed on last few classes. So on that classes we have given that why this stability derivatives have been using for finding out the aircraft stability and what is its importance on finding out the stability criteria for an aircraft control systems and how that systems have been designed with this by using this stability derivatives also we have discussed in last few classes. So on that first one we have given like what is the longitudinal static stability derivation for part 1 part 2 like that we have given on the part 1 some of stability derivatives for CXA and CFA and CZA and CZX. And the other part 2 also we have given CMA and CMZ and CMX and CMA also CM alpha also we have derived. So now if we we got that equations for longitudinal stability, and now we are discussing the solution for that equation, like taking one aircraft conditions and its data table. So based on that data table of an aircraft, jet aircraft, we have deriving that solution for that longitudinal equations of motion. So let's go into the topic. So see, this equation you've seen now. I told about this equation only. So the about this equation we have already we have given explanation about the stability derivatives that here you can see that CXU and CXA and CZA and CZU and CZQ and CMA and CMQ. So for these stability derivatives, we have and here CM alpha also there. So for these stability derivatives, we have already given explanation on previous videos. So on that videos, we have given stability derivatives explanation in the sense of by considering the elevator deflection and the rudder deflection. Radar deflection and its usage. Usage means what? How that stability. If that downwash velocity. We have discussed about the downwash also. So the downwash means was due to the wingtip vortices. Like whenever the flow is flowing over that wing leading edges. Wing leading edges. So like here, so we will get a high pressure and low pressure mixing up. We can generally aircraft will aircraft will experience that low pressure and high pressure mixing velocities at near the tips. So due to that mixing velocities here the vortices will be formed. So due to that vortices there will be adverse pressure differences will be happen after the turbine. So that adverse pressure differences will be continued to this tail also. Here the tail is there. So if these wingtip vortices will be continued till this tail also. Due to that adverse pressure gradient adverse pressure changes continuing up to that tail. So there what will happen generally for generating the lift, what is the required condition is the downward pressure should be high and upward pressure should be low. So then only we will get a lift in a required position. But due to this downward, due to this wingtip vortices, there will be a pressure changes on upward and downward. If you compare the pressure changes from upward and downward forces, so the downward pressure will be low and upward pressure will be high due to that sudden change in velocities. Like if the vortices have been forming out, these vortices will be continued up to this tail also. So there the downward velocities will be adversely high. So due to the downward velocities, high velocities, what will happen whenever the velocity is high, though, so that the pressure will be low. So if that downward pressure is low, then what will happen? There will be an adverse change in lift also. If you giving that elevated condition, elevated deflection also, there will be a changes in lift. So if these conditions are happen, how this stability derivatives will be how this stability derivatives will be performed at this condition. What is its behavior at this downward condition? So that downward condition is due to that linear velocity u and that angle of attack a. So also with the change in pressure also, the dynamic pressure q. So with this this x will be defined as the linear equation. That means in a linear axis, like if you say that the body axis system, like this is the body axis system of an aircraft. So for this aircraft, this will be the x-axis, and this will be the y-axis, and this will be the z-axis. Z-axis will come downwards. So there will be a changes. Normally, we will consider the changes in linear equation and linear direction and downward direction. So that linear direction stability derivatives will be defined with x notation, and the downward direction changes will be notated with the z. So these linear equations, linear direction changes will be with respect to velocity and with respect to angle of attack. So that with respect to velocity and angle of attack, we have called it as u and alpha. And for the same as for z also, there will be changes with respect to that downward velocity q, the downward velocity q, and here the pitch changes are there, so that angle of attack alpha is alpha also will be included in this one. So that means what this x and z are the linear forces acting on that direction. Due to that linear forces, what are the stability derivative behavior? And this m denotes for, this m is for what? This m is for the momentum due to these forces. Like at the aerodynamic center, if we call it as this aerodynamic center, and forces acting on this axis, due to the forces acting on that axis will be give a momentum about that axis. So that moment is called it as a cm. So that moment also will be with respect to that alpha and q. So that also we have considered here, and we have given the explanation for that also. So for this, all these conditions we have already given. If you see that previous things, so you can have a, if you refer the previous videos, you can have a reference for what is the stability derivative for cm alpha, what is the stability derivative for cmq, and that you can see on that video. So by using on that, here what we are saying is like, so we have a big equation. That equation is contains that linear equations, linear stability derivatives, and that z-axis stability derivatives, and the stability derivatives with respect to momentum changes. So that all been included in this one. And this theta also is related to that pitching moment only. That pitching moment, again we have considered in big theta. That means if a flow is flowing over, if flow is flowing over here, and there is an incidence angle with respect to that flow also. That actual angle of attack we have considered with theta, and that incidence angle we have considered with alpha. So with respect to that angle notation also, we have given what are the things required in this equation also, we have already explained. So each and every axis, I mean each and every equation, like see here, this is the first equation. The first equation is containing only that axis direction things only. I mean the linear direction values only. And the second equation, if you see, so in this second equation, so there is a axis. I mean there is a contents with respect to z axis only. So here you see that z axis z axis values only we have considered here. And after that, the third equation. This third equation, if you see, so in this third equation, everything is related to momentum only. So that Cm alpha, Cma, and Cmq, these are all related to momentum things. So these three equations are related to three types of axis notation. So that means linear axis, that downward axis, and the four moments with respect to that forces. So those things only we have. I mean those things only consider in this equation. So by using this equation, how that elevator deflection, rudder deflection, and how this stability derivatives will be. I mean the Cm alpha, Cm q values will be effective on designing that aircraft stability. We will going to see now. So let us take one aircraft having different. Having a data sheet. Aircraft data sheet is having this much of values. This has been taken from the. This has been taken from automatic control of aircraft by Blackdown. So first reference already I've consider. I mean I've mentioned that book also here. If you see on the later on, you can see that book. So on that book, I've taken the data sheet values of an aircraft. So this is an aircraft is having the theta values is 0, and it's having Mach number is 0.62. That's a subsonic passenger aircraft only, and its maximum weight is 5,800 slush, means almost if you convert into our our UG, SI units, it will be around maybe it will be around some 4 to 5 tons, like that. So and its velocity is around 600 feet per second. That means 600 feet per second means how much it will be. So 1 feet is for 3 meters, it is 1 feet means 30 centimeters. So that means around it will be some 400 or 450 meter per second. 400 or 450 meter per second velocity. And the S that total total area also, that wing area here, you consider the wing area. That wing area is 2,400 square feet. And this IY, that IY will be like what that sludge per feet square. So that is around this is around 2.62 into 10 power 6 sludge per feet square. And now that we have given the values for CXU, CXA, and CW. So that CXU and CW can be taken out from that direct formula substitution only. So that is CXU, you can write it like -2 CD. So that CD value for this is already around a 0.44. So if it is a 0.44, then the CXU value will be minus 0.088, and the CXA will be coming from dou CD by dou alpha, and the CD will be taken out from this equation. And CD thing also we can take it out from the data sheet, and the CL values also we have taken out from that aircraft data sheet also. That is around 0.392. And CW is mg by sq. So mg and sq have been already we have given here. That values are around minus 0.74. And this LT by C, LT by C also we have taken from that data sheet only. That is 2.8. And C is chord. So chord is around 20.2 feet. And CZU, that is CZU means what? So already CL we got it from here. So to CZU is around minus 2 CL. So that value is around 1.48. So we got a values from the data sheet, and the formulation of the values already we got it from the equation things. So these are the values we got it for things. And next thing will be about CZA. So that CZA, if you find it out from the CZA thing, if you see the explanation for CZA, the DCM by DI, and CM is around CM is again it will be US. I mean, sorry. So CM is what? CM is again USQ. SQ USQ USQC will be there. So if you remember that equation, so from that we have a CM definition, and this elevator deflection angle, that is epsilon. So that deflection angle, that deflection variation also we have considered. So that value is around how much? That is this value is minus 1.54, and that d by d alpha is 0.367. So and into 2 it is included on the formulation. So the total value will be what? Minus 1.13. And similarly, CZD will be what? CZD is dou CL by dou alpha minus CZ. The dou CL by dou alpha we can take it from CL values, and CD values also we already got 0.04. So if you substitute that value, so we will get minus 4.46. So these are all values you can get it from that data sheet. And appendix if you see it on the back side of the textbook, you will get the values of CD, CL, and all. And from the internet also you can get the values for this aircraft. Okay. And that CZQ also take it from 2K into DCM by D alpha. So the DCM by D alpha is already we got 1.54. So if you multiply that one, we got minus 3.94. And the CME is again DCM by DI into D by D alpha into L by C, LT by C. So that LT by C also we have substituted here, and the total value is how much? 3.27. And the CMA value is how you can get that S into M, that S we got, and M also we got. So from the S into M, and DCL by D alpha value also we got 4.42. So if you see here, so if you substitute that values from here, you will get minus 0.619. And the CMQ is what? 2K into DCM by DI into LT by C. So the DCM by DI value already we got it from here, that is 1.54, and LT by C is we have taken from here now. So if you substitute that value, we will get minus 11.4. So we got each and every value required in this equation. If you see that equation, every value we will get it from that. That explanation of values only we have given here. So after if we get the values from this one, so the k values, like previously we have didn't given that k values. So generally k values you can assume like 1.1 or 1.2. So then that if you substitute that equations in if you substitute the values in required things, so here q is what? Dynamic pressure, that is half rho u square, and rho rho value is 0.20585 pound per feet cube, and this u is what? 600 feet per second is there, no? So that values, if you substitute that, we got dynamic pressure is how much? 105.1 into 105.1 pound per square feet. And other values also mu by sq. So mu by sq also we got, we need it here, no? So that mu by sq values also we have we can calculate from the given values. And c by 2u into CZA, that CZA values we can take it from that. And here everything is in seconds only. If you if you see that, if you see that values, that dimensional modulation for this one. So M is what? So M is in pounds. So M is in slugs or pounds. So that is LB, and this is feet per second, and this is for S is feet square, and Q is LB per feet square. So LB per feet square is how much? So this will be, LB will be there, and only that again one more feet square is there, no? So if you cancel out that one, we will get in terms of seconds only. Everything is in seconds only we will get. If you multiply that also, if you see that also, you can get it from this thing. So ultimately, we will get it from seconds only. Okay, so per seconds. So like that for everything, if you substitute the values in this one, so we will get that cu by cz q value is 0.066 seconds, and c by 2u into cm alpha will be 0.0552 seconds, and c by 2 into cmq will be how much? Minus 0.192 seconds, and iy value by sqc value, if you see it here. So this is how much? 0.514 second square. So if you see that iy things also, sludge per feet square. So sludge per feet square, and s is in feet square, and this is for lb per feet square, and c is in feet. If you see that one also, you will get per second square things only. In terms of second square only, we will get, right. So this is the things for values. We will get it from other values like cm, that cxa, cxa, and czu, and cza, and czq, and cma and cmq also, we are values we got, and this iy by sqc, and c by 2u into this one, and c by 2u into these values, and other mu by sq values also we already got it here. So if you substitute all these values in that equation, like if you substitute all that equation values in that equation, so first also there is a Laplace, that Laplace equation for if you apply the Laplace transform for that differential equation, because this is the differential equation only. If you if you convert that into Laplace transform, we will get a in terms of Laplace operator, that is S. So if you multiply, if you substitute all that equation, and if you got the final equation is, so first one is what? So 13.78 S plus 0.088 US plus, minus 0.392 alpha S plus 0.74 theta of S, and second one will be what? 1.48 U prime of S, and 13.78, and 4.46 alpha prime of S, minus 13.78 theta of S, and third one will be what? First one is 0, then second one will be in alpha, as alpha prime S will be 0.0552 S plus 0.619 alpha S, plus 0.514 S square, plus 0.192 S of theta of S. So in terms of that, we got the values for this thing. So now we got three equations. So the only that solution we will get it from here by getting the roots for s. If you get the values for s, then only we will get a solution for that equation. So for finding out the values for yes, so make it as a matrix form. So for that matrix form, make this as for that matrix form, find the determinant of that matrix and equate it to 0. So if you find the determinant of that matrix and equate it to 0, then you will get a equation like this. So like it's a simple mathematics only. That will be what. So first one will be like 13.78 s plus 0.088 into so this into this one. So this into this one, if you see, so what it will be 0.514 s square plus 0.192 s s into 13.78 s plus 4.46 minus of 0.0552 s plus 0.619 into minus 13.78 s. So if you multiply this all these values, and it will be like as a cube, and as per 4 values we will get. So that total value, I mean, this is one thing, and another one will be minus of minus 3 point, I mean 0.392 into, so this into this one. So first one will be 0 minus 1.48 into 0.514 s square plus 0.192 s plus 0.74 into this into this one. So that will be like what, 1.48 into 0.0552 s plus 0.619 0.619. If you multiply all this thing, so you will get the equation like that. That too, it's a fourth order quadratic equation. So see here, so 97.5 s power 4 plus 79.79 s cube plus 128.9 s square plus 0.998 s plus 0.677 will be equal to 0. So this is a fourth order quadratic equation. So this fourth order quadratic equation can be, I mean, it has to be solved. That means it will have a 4 roots, right? So it is a fourth order, means the s will have a 4 roots. So if you write it, I mean, if you take it common with 97.5, so that final equation, I mean, if your final equation will be like that. So s power 4 plus 0.811 into s cube plus 1.32 into s square plus 0.0102 s plus 0.00695 s 695 equal to 0. So here we need to determine the magnitudes of u prime, alpha prime, and theta. So the I mean, if you consider the transient response of these variables at the time of variation, at the time of variation, so that response will be like if u prime of s means what, u prime means it's again a differentiation only. So that a differential equation, if you again solve it like a higher order differential equation or a second order differential equation. So the solution of separate equation will be like what, a1 e power m1t and plus b e power s2t plus c e power s3t and d e power s4t. So it's like a common solution and particular integration. That thing will be, if you remember that solution of a differential equation from two solutions. So this is the common solution, and that the particular integration values also we will get. So that particular integration values, how we can get, again, if we get the roots of this equation only. So if we get the equation roots, then we will substitute on this one, so that we will get the response of that value. So to obtain that roots, what we need to do, there is a conventional method like Lin's synthetic division methods. So in this first we need to assume one value for yes. If you substitute that value on that one, and then if it is equal to 0, then that value will be I mean that value will be root for that this equation. So based on that equation, again one more value will be substitute on that s, and again we will get two values. So if you get the two values, and the other if you want to get the other values from these two, I mean you can't substitute each and every value on that equation and you can get the roots. So for that, what we need to do, we need to use a synthetic division method. So that division method is like this one. So if you see that 1 plus 0.007 and 0.0053 are the roots of that, yes. And if you do the synthetic division method for this one, so what it will be, so first you get the coefficient of each and every I mean coefficient of that equation is what, first s power 4 coefficient, after that s cube coefficient, after that s square coefficient, s coefficient, and constant. So if you are getting that values here, and after that what we need to do, so first we need to divide with this one. So first, if you make it with each and every value with this one, so you will get. I mean, if you divide this one, this will be gets 0, and a 0.88811 minus 0.007 will be like what, 0.8033. And if you divide this one, 1.3147, and here there is no values, as it is, it will come here. So as it is, it will come here. After that, one more value we will make it after that. So now we will get that division values are what, 0.833, 1.3147, and 0.0102. So if you again multiply these values with this one, and if you substitute here, so we will get 0.8033. I mean, first value will be as it is, first one, and second value will be, if you multiply with that one, it will be like what, 0.0062, and here it will be 0.0041. And again, if you divide that one, we will ultimately get these values like this one. So see here, here the differences will be I mean, almost very low. So for the next, I mean, if you continue this one to by next division, so for the next division, what is that one? So 1.3085 plus 061 and 69 will be divided by 1.3085. So you can say like 1 plus 0.00466 plus 0.0053. So if you again, I mean, if you divide it with 1.305, we are get another set of values. So if that, with that set of values, if you do that synthetic division again, so you will get this values. I mean, ultimately we got a value of 0. I mean, the same thing only, same method only we have. I mean, same method only we have considered here. So if you do that one, we will get a ultimately that 0. So that means what? What are the two? I mean, square root values. So first one will be, so 0.00461, yes, plus 0.0053, and second one is what, 0.806 806, yes, and 1.311 s plus 1.311. So that will be equal to 0. That means what? Yeah, that the quadratic, fourth order quadratic equation is divided into two equations. That is in second order equation only. So this second order equation, if you make it like in a common way, if you write that quadratics in that to indicate the neutral frequency, that is omega and damping ratio zeta. So if you substitute that omega and damping ratio on that equation, so what is the, I mean, if you compare with that equation, what is that actual equation? S square plus 2 zeta p and omega n p s plus omega n p square. And another one equation is also omega ns and omega ns square. So if you compare with that previous equation, so zeta s is what? So zeta s is here, you see 352, and omega ns will be 1.145, and I mean, like if you compare with this here the coefficient is 0.000466. And here the equation is 2 zeta 2 zeta p omega and p s. So each equation, if you compare with that thing, I mean, if you compare the coefficient with that one, so you will get values of like that zeta p will be what 0.032, and zeta s will be 0.352, and omega ns will be 1.145, and omega np will be 0.073. So these omega n and omega ns and zeta s and omega p and omega p and zeta p, we call it as a short period oscillation and phugoid oscillation. So what is short period oscillation and what is phugoid oscillation? I mean, phugoid approach and the short period approach also we will see it in coming classes. So this is what here we are getting the response of that equation in terms of that angular. I mean, here omega. So if you see that omega ns is in radian per second, and zeta is a constant value, so we got this value. So that means here the oscillation having a frequency and its range. So here the frequency and range values are being here. So if you see that one, I mean, here what we are ultimately we are getting for an aircraft with a data sheet of having different values and different different angular conditions. So if you get the solution for that equation, we are getting that oscillation values only. So these oscillation values, why these values are significant means whenever there is a if you want to find out the its response frequency responses for a small control stick input, so we will get a, so whenever if you give whenever if you give values uh, for an aircraft speed and its range, I mean aircraft speed and its stability derivative conditions, so you will get a values of like that. So these values will be gives you that when if you give a small perturbation in the control system, you will get a response frequency response are like this. So the characteristics modes are nearly all the aircraft most flight conditions are two oscillations. So one is the short period with the relatively high damping. So short period means what like maybe in a sinusoidal short period waves, and due to this damping, other long period with very high light damping. So long period means what? So there will be like this. So there is a long period oscillation, but that oscillation is having a very high range. So the damping range is very high. So the periods and damping of these oscillations are very vary from aircraft to aircraft. So with the with the flight conditions also. So that the short period oscillation is called as a short period mode, and primarily consists of variations in alpha prime and theta. So that means whenever if you're giving a giving a control surface movement to change this alpha and theta, so that we will get this type of oscillation. That means whenever you are giving a control stick position to like that, so there will be a changes in that aircraft total stability in terms of that frequency variation. Frequency variations means what? So whenever it is getting that perturbation to that cruise condition, so after coming to that cruise condition also, it will have a, I mean, it will take a period to come to that original condition. Will get a frequency response of like that. That means this much of frequency for if you see here that 1.145 radian per second means what? There is a change in that angle with the velocity orientation is 1.145 radian per second 1.145 radians changes have been coming. So for the 600 feet, I mean around 400 meter per second 400 meter per second I mean 400 meter per second means around if you see, So that 400 meter per second into some 18 by 5 you see. So that will be around 80. So 80 into 80 around 900. Some 900 or 1200. So how much it is? 18 into 8 will be 8, 64, 4 and 8, 8 to 4, 1400. That means 1500 km pitch. At that 1500 km pitch speed, if you give a small throttle changes on small throttle changes for change this alpha and theta, you will get a frequency response of this much. So this is called short period and short period mode of oscillation. And that Fugite mode will be thought as an exchange of potential and kinetic energy. So that aircraft tends to fly sinusoidal flight path in vertical plane. So as the aircraft proceeds from highest point of the flight path to lowest point, so it peaks up speed and thus increasing the lift and wing lift of the wing and curving of the flight path until the aircraft start climbing again, and the velocity decreases. That if the velocity decreases, that lift also decreases, and the flight path curves will be downward. That means the flight path curve. If you see here, so here it will be like this. It may come like that. I mean, not like this much peak. So it will be like I mean, if you see that fugite mode will be, so suddenly goes up and goes down, goes up, goes down, goes up, goes down, and ultimately it will come to that original position. So within that variation, what will happen? So that the downward velocities also will be sudden changes, and lift also will be suddenly it changes. So if from that changes, if it is come to its original position, it will take some time. So as here the lift decreases and the velocity also decreases. So this condition will continues until the motion is damped out. Damped out means this variation will be, if you variation will be coming nearly, and if it is if it is coming to original position, so that means what, here the dampings are totally zero. So then which generally requires a considerable number of cycles. So that means if it is come to that original position, it will take a time for getting that cruise normal cruise condition. So however, that period is very long, and the pilot can dam the fugite successfully, even if slightly divergent or unstable. I mean, if it is this much orientation, I mean, if it is this much of frequency orientation is there for damping also, pilot can overcome that damping and make it into the stable condition. If it takes the time also, he will make that into stable condition after some time. So with this, what we are saying, like a stability condition, I mean, in a linear equation of motion, we are using for getting the changes in that alpha and theta and momentum also with respect to the flight data values. I mean, when we are giving the flight data values, we got the stability derivative values. After that stability derivative values, what are the frequency response of that total aircraft also, we got it with a short period oscillation and fugite oscillation. So I mean, with a small change at that speed will gives you this much changes in damping. So to avoid this, what we need to do, that control surfaces will be that control surfaces will be designed in such a way that that field should be given to that pilot. Like if you are suddenly giving also, that sudden changes in control surface or control surface operation won't be there. It will be like a gradual variation only. For that gradual variation, there will be an electronically operated system is required for that one. So if that electronically operated system is perfectly, perfectly if it is matching, I mean, perfectly if it is, perfectly if it is operating, then only this type of damping will be avoided, so that the aircraft will be always flight in stable condition. So if you see furthermore about this one, you can refer that that book, Blacklock JH, automatic control of aircraft, automatic control of aircraft and missile. You can get a more details about that one. Okay, so these are the other relevant books also I followed for finding out these things. So this is about the solution of longitudinal equations of motion, and next class we will discuss on that lateral equations of motion and its significance. Okay, thank you.
Like, share, and subscribe. Hit the bell icon for more updates.